Welcome, and we are studying oscilloscope. So in our last class, I tried to demonstrate how an cathode ray tube oscilloscope work, its construction and working principle we talked about. So let me recap very quickly. It is made up of a glass tube, evacuated glass tube with an electron gun. Basically, this is a cathode ray tube. This is the cathode which emits, which is heated up. I'm not going into much detail. Okay, so electrons are emitted, then we have some arrangement to focus it, make it a narrow beam, etc. And then this essentially passes through two sets of plates. Okay, one we call the vertical deflection plate, and another is the horizontal deflecting plate. Okay, now this between these two and these two plates you can apply some voltage difference. Therefore, the electron beam will get attracted towards the positive plates, and instead of going straight and hitting the center, it will hit some other point. Wherever it hits, a bright spot appears there. And if you are changing these two voltages here and here, then that spot will move continuously on the screen, and that can generate patterns like sine wave, etc. In the previous class, we have taken a specific example where we apply this ramp signal across the horizontal deflecting plate and the sine wave across the vertical deflection plate, and therefore we saw that the spot moves in the form of a sine wave like this. Okay, and the sine wave appears in front of us. That's how it works. Okay, and so now if you just want to measure or see any other waveform, okay, so basically the waveform that you want to visualize is to be applied across the vertical plate here. So this is where you apply the waveform which you want to see. Okay, and we can have amplifiers before that, amplifiers or attenuators, and we have studied a lot of amplifier circuits. So by changing the magnitude or the amplification of this voltage, we can change the height or amplitude of this wave. We can make it larger or smaller by having an amplifier before applying this voltage at this point. Okay, so that's easy, but one important observation is that this signal, this ramp signal, which is also called the time based signal, this is also important to have this pattern displayed, because essentially this moves the spot from left to right, back to left, again left to right, back to left, and so on. Okay, so this is therefore very important. Okay, so the ramp signal or the time base must be synchronized with the frequency of the input voltage or waveform to have a nice display. Okay, say for example, for example, I can take the same time based signal. Let this be the time based signal. This is the 0 level, and say previously I had the sine wave which was like this. So it used to complete one cycle within one period of this time-based signal. But if say instead of this I have another signal, sine wave, which completes two complete cycles within this period, then how will be my display? Okay, so I request you just give a thought to this. If this is my input signal which is applied to VH horizontal plate, then the display will of course be like this. We start from extreme left and then we go to the right from here to here. Call it T0, T1, or call it T2 and this point T1, middle point. Then as we go from left to right, we first go down. So from extreme left, we will first go down here and up and to 0, down, up and to 0. This is T1, and then we will continue to go to right, but one more cycle, down, up and 0, down, up and 0. So we shall see this pattern. We shall see two cycles on the screen, right? So but now suppose let's take another example. Say the input time base is like this. One period, second period, okay, and this is the 0 line, 0 voltage line, time axis, and say the input signal is not synchronized with this frequency. Say what we have, the input signal say completes half cycle here, then quarter cycle here, then another quarter cycle, and then half cycle here. So we have 1, 2, 3 half cycles. So we have 3 half cycles. Okay, see 3 half cycles means 3.5 cycles of input is equivalent to 2 cycles. Okay, this is 1.5 and this is 2 cycles of ramp. So how will be the display? Okay, don't watch my answer, plus before that think yourself, then verify with my answer. Okay, so think please. Let this be the screen with divisions marked. Now say we mark some points here, T0, T1, T2, T3, T4, T5, T6, all the corner points, all the 0 crossing points I am just marking. Now at T0 you see we are at the extreme left, so say we are here and height is 0, so we will be here. Then as time progresses, at T1 we will be at the center of so we will be here somewhere on this axis, and the height you see is this much. Okay, so we will go that much. So the spot will be here, and sorry, not this much, I made a mistake, this much. Okay, maybe that is this much. So we have gone like this. Okay, and then at T2 we will come back to 0 and mm, okay, and here, so at T2 is somewhere will be here. X position will be somewhere here, not totally right, somewhere here. Okay, so so then this will be the pattern, okay, at T2, and then we will go down further. Okay, so this will be the point T3, where when we are at the extreme right, but height is negative. So this is point T0, T1 somewhere here. No, T1 is here when we are at the center from according to the on the x-axis. Okay, this is T1. So that point will be here somewhere, and this is T2, this is T3, T2, T3. So we will have a trace possibly looking like this. Okay, and then what will happen? After that, at T3, we will come back immediately to extreme left, but the height will still be negative. So from here, we will come back immediately here. This is the same time T3. So we are here, and then we will start to traverse again to the left to right, and then we will go slowly up, cross the 0 at T4, and then half cycle like this. Okay, so this point is T4. T5 is the point when x position is at the center, horizontally at the center. So this is T5. So this is the plot that we shall see on the screen. Okay, and this has happened because these two are not properly synchronized. So we will not see the sine wave correctly. Okay, so like 1.5 cycle here, and another 1.5 this is like half cycle plus quarter cycle. Okay, plus another quarter cycle and a half cycle is here. Okay, and okay, then what will happen? Let's extend. So let's see what actually happens after this. Say this is the next, these are the next two cycles of the ramp signal, and the input signal will complete half cycle, quarter cycle, another quarter cycle, and another half cycle. Okay, after this point I need not consider anymore, because after this point the situation will be similar to this. Okay, but before that, let's see what will you see here. So you'll start from extreme left, go down one half cycle and a quarter. So go down, it will possibly look like this. My drawing and scale etc. may not be accurate, but roughly it will look like this. And then again we'll start from extreme left here, go towards the right, and simultaneously have to come down and up. So we shall start from here. No, here. Okay, so this is uh, I guess I made a mistake previously. So this is half cycle. No, it's correct. So this was the previous path. Let me make it a different color. Okay, so this is this portion, right? This is this portion, and then we will have this portion. Let me use a different color, which will come here as starting from high value of high y-axis. We go down first, and then a half cycle. Okay, so this will be the complete pattern. Although I have drawn it with different colors, but you will not see with different colors in an oscilloscope. Everything will be of same color. Okay, so this has happened because of non-proper synchronization between the ramp and the input sine wave. Okay, so this way you possibly can draw different patterns for different frequencies of the input and the different frequencies of this ramp. Okay, so two important things. So synchronization is important, and we will not have time to talk about how exactly the synchronization can be achieved automatically. You can study this from the books, and if you are interested, we will make possibly additional videos later on. But okay, we will talk briefly about at least how the ramp signal is generated. We shall talk about ramp generation briefly later. Okay, because this ramp signal is very important. We have seen it being used in different cases, like those voltmeters, digital ramp type voltmeters. There we have seen ramp signals, right? So ramp signal is used in many different instruments that we have studied. So we will talk briefly about ramp signals soon. Okay, but before that, let me just talk about another interesting thing, which is what happens if you apply two external waveforms or signals across VH, the horizontal plate, horizontal deflecting plate, and vertically deflecting plate. What happens if you apply two voltages from outside? Okay, so far what we have talked about is this. Here we apply, so here across VH we will apply a voltage from outside which you want to observe or see on screen. But sorry, across VV, vertical one. Here we shall apply the external voltage from outside, and across the horizontal one we will apply the time based signal or the ramp. This ramp, this goes to VH, this, and VV is from the waveform that we want to see. Now in oscilloscopes we have provisions to apply two waveforms at across these two sets of plates. Instead of applying this ramp across this horizontal plate, which is generated internally in the oscilloscope, we can apply an external signal across this plate as well. And then we can see a lot of different patterns on the screen, which is called Lissajous plots or figures. Okay. So basically, so what do we do? Say we have these two sets of plates, one, and this is the horizontal one. Electron is flowing through it, and we are applying a voltage VV. Okay, let me call it Vy, because this voltage deflects the electron beam along the y direction vertically, and between this we have a voltage, call it Vx, and the electron beam is flowing through this and hitting the screen. Okay, so this is the arrangement, right? This is the side view of an oscilloscope. Now, suppose I tell you that Vy, which is this, across this, is given as, say, sin omega t, and Vx is equal to, also let me call it, this is a sin omega t and this is b sin omega t. Then how will the display look like? Let's see. So let this be Vy and let this be Vx. This height is b and this height is a. Okay, and let me draw the screen. So can you tell me how will the spot move on the screen? Say at t equal to 0, the vertical position or y position should be 0 and the x position should also be 0. At t equal to 0, so here you see both x and y 0, so that means the spot will be here at the center. Then as time increases, the y position increases, x position also increases, and you see y position and x position are proportional to each other. Okay, at say this time, if I call this t0, this is t1, so at t1 y position will be maximum, x position will also be maximum. So we will have y position here, this height will be proportional to a, the amplitude of this wave, and this will be proportional to b, the amplitude of Vx. Okay, this is Vx, this is Vy, and from here to here the dot will traverse like this. Okay, so this is how the dot will go like, and after that, so starting from here, you see the height decreases, x position also decreases and comes to 0, So the dot will come back like this again here. After that, the y position becomes negative, x position also becomes negative. So we will go like this up to this point. So let me mark these points T2, T3, T4. So this was T0, T1, T2 again here, T3 is here, and then from T3 to T4 we will go back. Height will decrease, x position will decrease. So we'll go like this. Okay, so then that means we'll go like this, come back, this, come back, and this will repeat. So this is the plot that we shall see on screen, right? Okay, now let's take another example. Where say I say that Vy is or Vx is as it is, but I'll make Vy cosine omega t. So then this will change. This will be like this. It will start from value a, and so this is how the pattern will be. Okay, so now let's see how this looks like. Okay, say at t equal to 0 here, at t0, x position is 0, but y position is given as a, positive. So the dot will be at t0 somewhere here. X position 0, but height is positive. Then as time increases, x position will increase and y position will decrease. So from here, x position will increase, so we will go towards the right, but y position will decrease, so we will come down, and this will look like this. Okay, so this point is t0. At t1 we have height 0 but x maximum, and this is proportional to b. So this will be equal to b, proportional to b. And then from this point onwards, so this is t1. So after t1, what will happen? Let me change the color. So after t1, height goes to minus, negative, x decreases to 0. So this will be like this. And at this moment, t2, height is minus a. So this height is proportional to a here, and x is 0. And after this, what will happen? Y will go back to 0 and x will be more and more negative. So we will move like this. Okay, so this is the point t3, and after t3, x becomes 0 again and y goes to positive like this. My drawing is not very good, but this will actually look like an ellipse, perfect ellipse. So this will be an ellipse. Okay, and you can also verify this I mean, you can say, for example, you can write the equation as Vy, so from this divided by A, take a square of that, and plus Vx by B, take a square of that. This you can definitely write as, so what is Vy by A? Vy by A is cos square omega t, and Vx by B is sin square omega t. This is equal to 1. Cos square plus sin square is equal to 1. So this is the equation of an ellipse, right? Okay. So this way you can generate lots of different patterns, and you can also measure, for example, the ratio of the these two amplitudes. Okay, so from the pattern, Lissajov pattern, you can measure the ratio of two voltage amplitudes. For example, in this case, this is the amplitude or twice of the amplitude of the signal applied to the to the horizontal plates, and this is the amplitude of the voltage applied to the vertical plates. So from this height and this width, you can get the ratio of these two amplitudes. You can also get the ratio of frequencies, and okay, let's talk about the ratio of frequencies. Okay, so let's take an example. Say I have this varying at a double frequency. So I will make it, so I will put a 2 here, 2 omega t. So that means it will complete one cycle, another cycle here. So one cycle, one cycle here, and another cycle here. Okay, so now let's ask, how will this plot look like? Please do not watch my answer before trying it yourself. Okay, so once again we will start from, say, t0. At t0, x position and y position both are 0, so we'll be here. Then you see x position increases, y position also increases up to this point. Okay, so we will go towards the right and up. Here, so maybe like this. I'm not claiming that this is going to be a straight line. Okay, this will not be a straight line, but it will go, we know that from here we will go towards the right and upwards, and this point, call it t half. This is the point t half, so this is t0. T half will be somewhere here, and after t half, height will decrease, but x position will keep increasing. So That means we'll go towards the right and down, so we'll come somewhere here. Okay, this will be T1. This is T1. After that, what happens? We go down and X position also decreases. So X position will decrease and we will go down like this. So here we will have this point, call it T 1.5. T 1.5. This is this point, right? After that, what happens? Y increases, goes to 0, and X decreases, goes to 0. Y increases, goes to 0, and X increases, goes to 0. So this point will be T2. So the pattern will actually look like this. I told you those will not be straight lines. So this will go like this. Okay. And after that, what will happen? After that, we will go to the left and up. So this you can continue yourself. You'll see this will look like this. So we will have a pattern like this, like a loop. Okay, and from this, just from this observe, okay, now can we find the ratio of the two frequencies from this pattern? Suppose we do not know a priori that these are the forms of Vx and Vy. Can we, suppose this is just given, we do not see this, so we start from this and let's ask what is the ratio of frequencies from the plot, from the Lisa-Joe plot. Okay, say how to, let me tell you how to do it. Say you start from here, okay, and make a complete traversal of this locus. So I start from here, and a complete traversal means this. Okay, start from here and go and this. This is one traversal, and in this way I have gone, you see, right 0, left 0. So that means one cycle of the horizontal signal Vx. Okay, you see, right 0, left 0. So this is one cycle of the horizontal signal or Vx. And what happens to Y? Up 0, down 0, one cycle. Up 0, down 0, two cycles. Once again, in one complete traversal, up 0, down 0, up 0, down 0. So two cycles. So we see that one cycle of Vx is same as two cycles of Vy. So we can write that Tx, time period of the Vx, is same as 2 times the time period of the Vy. Okay, and from this you can write that 1 by Fx is equal to 2 by Fy. Now, what is the ratio of the amplitude? You see, the amplitude of the x signal is how much? So in the x direction, I am moving this much. So this is 2 times b. Okay, this is 2 times b. And similarly, how is the y signal moving or varying? So this is, just observe, the y movement. Y movement is only this much. So this is the 2 times a. So you can read these values, this height and this width from the screen of the oscilloscope, and from that you can find the ratio of 2b and b and a, or a and b. Okay, so that's about the Lissajous plots. Actually, oscilloscope is a very interesting topic, and we can go deep and talk about a lot of different aspects of it. But due to the time limitation, we will not go further deeper into CRT oscilloscope. We will talk now briefly about only one important aspect about digital oscilloscope, digital storage oscilloscope, and we will conclude this topic on oscilloscope. So let's talk very briefly about DSO. How does a DSO work? A DSO doesn't have a cathode ray tube like this. This is not available, is not present in a digital storage oscilloscope. What does a DSO have? A DSO, roughly speaking, very brief, broadly speaking, works in this way. Say this is an input waveform, call it VIT. If this is the input waveform, then a DSO will have something called a sample and hold circuit. After that, it can have a digital voltmeter or analog to digital converter, and then we can have the display. What is sample and hold circuit? Functionally speaking, it is just like a switch. Functionally, switch, and maybe with a capacitor. Okay, so it's like this: switch with a capacitor. So this is Vi. After this, we will have a switch, and here we will have a capacitor C. So what happens, when this switch is open, then Vi doesn't affect this side at all. Now what we do, we close the switch for a brief while. Okay, so we close and then immediately open it. Close and open. Okay, so the switch is like it is closed. So if I write a timing diagram like this, so the switch is open. See, here it is open, then it gets suddenly closed and then opened. Okay, this is not a voltage waveform. So by this I mean if this is high, the switch is closed, okay, or on, and if this is 0, switch is off. So as a function of time, what I do, I close it for a brief moment and then open it. Then what will happen? The moment you close it, okay, a brief moment, this voltage Vi will charge this capacitor to a voltage Vi. Vi at the time t naught, which is, what is t naught? T naught is the time when you close the switch. Okay, so the moment, so this is the moment t naught if at t naught you are closing the switch, then whatever value of, so let me write VIT, not t naught, but here I will write VIT naught. Okay, so this is a time varying function. This is changing, this voltage is changing, but the moment you close it, that moment t naught, whatever is the value of Vi will go from here to here. Okay, and capacitor will be charged to that voltage. Now you then open it, and once you open it, the capacitor will remain charged at that voltage. It will not get discharged much. And therefore, after this, you see, we can have this ADC, etc. What is an ADC? This is basically a voltage measuring circuit. Okay, so this is basically a voltage measuring circuit. So this will then measure the value of Vi T naught. Okay, so this will measure the value of Vi T naught, and this will then pass this value in the digital form to a computer. Basically a DSO, inside it has some computing mechanism. So it will pass that value, the measured value of Vi T naught, to the computer, and the computer will then display that value on the screen in the form of an waveform. Okay, then what happens, after that I keep this switch open or off, and after say time gap tau, so this point is T naught plus tau, here I will open this switch again, close this switch once again, and then open it immediately. So then what happens, you close this switch again at T naught plus tau, this voltage is changing, this voltage is continuously changing, and you are closing this switch once again at T naught plus tau, then this voltage will come immediately to this capacitor, and the value of this voltage across the capacitor will get changed to the new value Vi T naught plus tau at this moment. Okay, and this value will then again be measured by this ADC, and this ADC will pass the value, measured value, to a computer, and the computer will draw a plot using the values like the voltage at Vi T naught. After that we got the voltage Vi T naught plus tau, and this way we will keep repeating it. So after this, say again after a gap of tau, so this instant, which is T naught plus 2 tau, we will close this switch again and open it. So this voltage, which is at that moment T naught plus 2 tau, Vi T naught plus 2 tau, will come here to here, and that voltage will be measured by this ADC, T naught plus 2 tau, and will go to the computer. In this way, we will have Vi T naught plus, in general call it N tau. N is 1, 2, 3, 4, etc. And these voltages are available to the computer. So the computer, what the computer will do? It will now draw a plot on the screen of the computer like this. So time axis, so at T0, the voltage was measured to be Vi T naught. So it will draw a point here. Let this be the voltage axis. So it will draw a point whose value is Vi T naught. After that, this ADC told the computer that the value of the voltage is this much at the moment T naught plus tau. So here at the moment T naught plus tau, the value of the voltage, whatever is that, say this is the value, Vi T naught plus tau, will be displayed here. So similarly, then at T naught plus 2 tau, some other value, call it Vi T naught plus 2 tau, will be plotted as a dot. And the computer, if the computer likes, can join these dots to give you a smooth plot instead of giving you this set of dots. Okay, So then you shall see that this is the waveform or how the voltage is varying. Okay, and so this is how it works. It basically measures the voltage at different instance, discrete instance, at t naught plus tau, t naught plus 2 tau, t naught plus n tau, and plots those points dot 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 like that, so on. Okay, and it can join it to give you a smooth plot if you like. Okay, so this is how it works, how a DSO works. So therefore, now say let me take VIT as this, a sine wave. Say this is VIT, okay, and okay, we call this tau. Tau is called the sampling period. Sampling period, and 1 over tau is called the sampling frequency. Why? Because as if we are taking sample measurement of the input voltage at that frequency. So we are not measuring the input voltage always. You know, the switch is not always closed, so we cannot see this voltage always. We can see this voltage only at those moments when this switch is closed. So we are taking samples. Okay, we are not measuring it always. So that's why this is called the sampling frequency, the frequency at which we are measuring the voltage, and this is inverse of that is the sampling time, sampling period. Now say here on the time axis I mark the points where I take the samples. Suppose I take the sample at this moment at t0, then I take the sample at here. That means at this moment I close this switch. Okay, the switch is closed here and then opened, here closed and then opened. So these are the moments I'm marking where I am taking the samples. And this gap is tau, sampling period. 1 over tau is the sampling frequency. So if so, now that means we will measure this voltage only at this moment, and my measurement will tell me that this is the voltage at t equal to 0. So the voltage will be measured to be 0. Then at t equal to tau, the voltage will be this much. This is the measured voltage. Okay. Here the measured voltage will be this much. Here the measured voltage will be this much. Okay. This green thing is the continuous time input voltage. Why continuous time? Because it exists continuously for all value of time. But this rate set of points, this we will call discrete time signal. This is a discrete time signal, discrete time measurement, because these values, these measured values, we know only at discrete values of time. We do not know, we do not measure what was the voltage at this moment or what is the voltage at this moment. So we only have the value here, here, here. So the computer will only draw these dots. It cannot draw this smooth waveform. Even if it joins these plots, it will join possibly like a straight line, like this. So it will join the points possibly with straight lines. So we cannot get exact detail or exact voltage between two samples. Okay, so therefore, the measurement that we do is not smooth, unlike a cathode ray oscilloscope. Cathode ray oscilloscope also have some limitations, bandwidth limitations, which we haven't talked about, but okay, leave that aside. Anyway, this is clear that discrete digital oscilloscopes will not give me continuous measurement. There is another fact, another important fact. That fact is that the measured value is not just discrete in time, it will also be discrete in the measured value. I mean, this is a ADC, analog to digital converter, which is measuring this voltage. And when a ADC measures a voltage, it discretizes or divides the range of voltage into small quantum, right? So for example, if I take for simplicity, let me take a 4-bit ADC, and if on this side, if I give a sine wave whose amplitude is, say, plus minus 8 volt, so this is plus 8 volt, here minus 8 volt, okay. This is a 4-bit ADC, so it can give you only 16 different outputs, and possibly it will map 0 volt, say like minus 8 volt, maybe this will get mapped to 0 0 0 0, okay. Then minus 7 volt will get mapped to 0 0 0 1, minus 6 volt will get mapped to 0 0 1 0, and so on, okay. Similarly, if you add 15 to this, so I think 7 volt will get mapped to this level, 1 1 1 1, okay. So you cannot get smooth output from the ADC. So what will happen is this. I'll just finish this in a few minutes. Okay, so this is the discrete signal which we have before ADC, okay, and the ADC will again, say, quantize it to a set of values, say the accepted values, let me zoom it, okay. Say this is Vi, okay. Say the ADC can give you only these levels, like this is 0 1 2 3 4 5 6 7, so on. So therefore this value, let me take a different color, this value will be represented as 0, so this will be represented as 0 0 0 0, okay, 1 2 3 4 5 6 7 8, etc. These are the levels, and this value will get approximated by possibly this. This is the closest integer, so it will come down somewhat below. So the value we will have here is possibly 1 2 3, 1 2 3. So 0 0 1 1. This point will be approximated by 4. So the value we will have here is 0 1 0 0, and so on. So you see, we have more error or more approximations introduced. The true value of the voltage at this moment was possibly 3.2, but the ADC will tell me this is only 3. Okay. Normally, I mean, so here I am assuming a 4-bit ADC. Of course, 4-bit is not a good number. A good oscilloscope will have much more number of bits than 4. Okay, so the approximation will be much lower, but this will be the situation. No matter how small is the approximation or error, there will be some error. Okay, so this is something you should know about digital oscilloscope, that the voltage is measured. Number one, voltage is measured only at discrete times, discrete intervals, and number two, due to the use of the ADC, there is some quantization error in the measurement. So we do not get perfect measurement, of course. Last one statement or one fact is this. Suppose if I have a signal Vi which is like this, and say if I am sampling it at a very low frequency compared to this input signal. So I am sampling one sample here, then say I am sampling another sample quite far, maybe here, and then maybe another sample here, and so on. So what will be my measured value? So my measured points will be this. After that, the next point is here. After that, the next point is here, and so on, right? So the oscilloscope will display only these points. It cannot display this intermediate pattern. And if the oscilloscope joins this dots with maybe straight lines, you know, this doesn't look at all like the original signal. This has happened because sampling frequency is quite less compared to the input frequency. And there is a theorem called sampling theorem, Nyquist sampling theorem, which says sampling frequency should be greater than 2 times the input frequency. This is called Nyquist sampling theorem, and he says if you sample the signal with a frequency twice or more higher than the input frequency, then you will get a proper shape of the input signal. Let me just demonstrate it very quickly. So this blue curve is the input signal, and now I will sample it at say 4 times of this input frequency. Okay, so this is the input time period. So I will take at least say 4 samples within each time period. So 1, then I will take next sample here, next sample here, next sample here. 1, 2, 3, 4 within one period, and then in the next period again 4 samples, 1, 2, 3, so 1, 2, 3, 4. Okay, and this is within one cycle, and then another 1, 2, so on. So how will the pattern look like? So this is one point, this is another point, this is another point, this is another point, this is, sorry, not here, this is another point, you just join these points. Now, if you join these points, you get a quite good approximation of the input signal. Okay. So, here sampling frequency is equal to 4 times input frequency. Minimum requirement according to Nyquist theorem is 2. We have more than that. Good oscilloscopes generally have more than twice of the input, the sampling frequency they take more than the twice, much more than twice of the input frequency. Okay. So, this is required, otherwise you will not get correct waveform. Thank you.